water and the room temperature. So after 10 minutes, it was very hot. So the water was 68 degrees higher than room temp, and then it cooled down. And then after 60 minutes, it was only 4 degrees warmer than the room. But the progression didn't seem linear. So if we want to make a scatter plot of this and test, we want to make a scatter plot. We want to see if this follows a linear model, and we then want to look at a residual plot to make sure. We'll be able to see from the scatter plot, but I'm going to have you guys make residual plots as well. So we're going to insert chart. Notice I selected the data. It gives us a bar graph, so in column chart down here in chart type, go down to scatter, and that's better. So it looks like the relationship is a bit curved. So it curves down. A line isn't going to fit super well, but let's put one anyway and check a residual plot. So I'm going to go to series, trend line, show R squared. R squared is actually really high, 0.836. R squared can be high without fitting a linear model super well. So this is one of those cases. So let's use equation. So this is our equation. The predicted difference in temperature is negative 1.2 times x. X is the value of time. And then plus 66. So if we want to make a residual plot, the first thing we're going to need to do is make predicted values with this equation. So if I say predicted temp up here, I'm going to enter in the equation that's on our scatter plot. So always start with equals for a formula there. And it's negative 1.2 times the x value. So I can just click on the x and then plus 66. So that says that after 10 minutes, our predicted temp was 54. And I can just drag this down and get all the predicteds. And now if I want the residuals, a residual is the observed value, so the actual value minus the predicted value. So observed minus predicted, I'll press enter, and I can just drag that down as well. So now to make a residual plot, I'm going to copy the time here, and then I'm going to copy the residuals here just so they're next to each other. And be careful to paste special and paste values only, because there's a formula here. So if you paste it here, it's going to change stuff. So notice that these numbers are the same. And if they're not, then make sure you're selecting paste values. So I'm going to select this, insert chart. Again, it gives me something I don't want, and I want to change that to a scatter plot. All right, so what we should see in a good linear model is a totally random residual plot. Some up, some down, there's no pattern. Here, there seems to be a pattern. It seems to be U-shaped. So we start way up here, we dip down, and then we go up. So in the middle, all of our residuals are negative, and it seems like there's a clear pattern. We could draw a curve through here. We don't want that at all. So this is a really, like a linear model is really poor in this case. Our predictions are in the middle. If you look here, our predictions are all higher than observed. So we're systematically making bad guesses with our linear model. So what we're going to do is try to re-express this data. So I'm just going to delete this, I'll delete all this. Rows 1 through 7. No, I want to delete columns. So what I'm going to do now, I'll delete this again, is instead of having the y value as it is, I'm going to change it up. I'm going to re-express it because I'm noticing that at first the y values are really high. 68 is really high, and it goes down to 4. So I'm going to try, the ladder of powers says square root. So first it says take the square root, and that's the direction I'm going to go, is down the ladder of powers. So I'll delete here. So the first thing I'm going to do is say, okay, I don't want difference in temp anymore. I want the square root of difference in temp. So square root of difference in temp. So I want the square root of difference in temp. To do that, I'm going to say equals square root, SQRT, parentheses there. I'll select, and I'll drag that down. So now we don't have the difference in temp, we have the square root. So I'll make a scatter plot of this. I'm just copying and pasting it to have the X and Y columns right next to each other. So I'll copy and paste special, paste values only. So let's see how this scatter plot looks. Is it as curved? Column chart, that's not what I want. I want scatter plot. It looks better. Let's put a line through it. So I'm down to series here, trend line. It almost looks like the same thing is happening. For all of these values here, our prediction is too high. The line is too high, our observed values are too low. So we're kind of systematically over-predicting here because we're trying to use this straight line, but in reality the data is kind of curved. So let's look at the R squared. The R squared is even better, so it's showing that we're getting closer. And let's look at the use equation. So it gives us an equation here. So I'm going to do the same thing, make a residual plot, and take a look at that. So let's do predicted. I'll just say predicted values. So again, I'm going to enter in the equation from the scatter plot. So the scatter plot says that the predicted difference in temperature is negative 0.123 times time times x plus 8.71. So I can drag down my predicted values, and now I can find my residuals. The residual equals the observed, what we actually saw, minus the predicted. And I'll drag those down. And now I will copy and paste to have the time as the x variable first, and then my y variable is the residuals. And I'll paste special, paste values only. So now let's make a scatter plot. Insert chart. That's not what I want. I want a scatter plot. This almost looks worse. So this is a very definitive U shape. It's a very clear pattern. What we don't want to see in a residual plot is a clear pattern. And that's what we see here. So this is showing that even though it looks better, the scatter plot looks better, the residual plot is telling us that a linear model is not working yet. So I'm going to climb down the ladder of powers again, and I'm going to try the logarithm. So I'll delete this. I'm deleting. What have I done here? I'll just delete all of this. Cut. No. Delete. Okay. So I'll delete this as well. So all right. Instead of the difference in temperature, now I'm going to take the logarithm of the difference in temperature. So log of difference in temperature equals the log. I'll use base 10. And let's always use base 10 of this value here. And then I can drag that down. Okay, so let's look at a scatter plot. So I'll copy, paste, copy, paste special, paste values only. And let's check it out. So insert chart, column type, or chart type, down to scatter. This looks much better. Just by the eye test, the scatter plot appears to be almost perfectly linear. So if we place a line to this, I'll go to customize series, trend line. It looks much better. So we'll show R squared. And R squared is very high. It's showing that 99.4% of variation in the log temperature can be explained by variations in time. So 99% of all these changes in temperatures can be explained by changes in time. Let's put the equation in there to make a residual plot. So here I'll have my predicted values. And again, I'm going to use my equation. So my equation says that the predicted log difference in temperature is negative 0.0251 times the x value of time plus 2.06. So I can drag down those predicted, and now I can find my residuals. Residuals equal observed minus predicted. So I can drag those down, and I will copy and paste time and residuals next to each other. Paste special, paste values only. All right, let's take a look at this residual plot. So chart, go to scatter plot. It still looks like it's a bit off, but the pattern isn't as intense. You can't draw a perfect U through it. So I would say it's much tougher to see a pattern in this residual plot. Compared to the others, it's much tougher to see a pattern here. So it doesn't look quite as perfect of a pattern. And if you look at the scatter plot, it looks like the linear model is much better. So we're going to go ahead and use this re-expression. So now, instead of using time in the y-axis, instead of using the difference in temperature, we're using the log of difference in temperature. So what this tells us is that our equation, I'll write that down here, our predicted log difference in temperature, which is also known as y hat, y with a little hat over it, equals negative 0.0251 times x, put a little x, plus 2.06. So if we want to make predictions using this equation, the question that I'm going to ask you guys is, what is the predicted difference in temperature? What is the predicted difference in temperature after 45 minutes? So we notice that our times here, it doesn't give us 45, but we can plug 45 in for x into this equation, and that's going to give us a predicted log of the difference in temperature. Then we're going to need to convert that into a difference in temperature. So I'll do the math down here. So my predicted log difference in temperature equals negative 0.0251 times 45 plus 2.06. So the value we get is 0.9305. That is not the predicted difference in temperature for 45 minutes. And if you look at these values up here, that makes sense, because at 40 minutes, the difference in temperature is 10. And at 50 minutes, it's 6. So somewhere in the middle here, our answer should be somewhere in the middle, somewhere between 6 and 10. So the fact that it's 0.93 is saying something's not right here. And what's not right is that we have calculated the predicted log difference in temperature. So we need to take this 0.93 and convert that into a difference in temperature. So the way we're going to do that, to undo the logarithm, is we're going to take 10 as the base. That's how a logarithm works. And we're going to raise it to the power of 0.9305. And that's not doing that here. I'll just use Google. So I'll say 10 raised to the power of 0.9305. And it's telling me my predicted value is 8.52. So even though the answer I got was 0.9305, that's not the final answer. That's the logarithm of the difference in temperature. Now we take 10 as a base and raise it to the answer. So 10 is your base.